Okay, so instead of writing a text, I'm just gonna explain quantum physics, and yeah, that will be easier for me, I guess, than write it down, because it's really hard for me to gather ideas to explain certain topics and more like science. If I don't know, I don't have any interaction with people, I think it's easier for me to explain it than write it down. So I'm gonna talk about quantum physics. Basically, quantum physics are interaction between particles, really small, smaller than the atoms and protons, neutrons, the smaller particles. So yeah, how they interact and how they behave and how weird they are compared to our understanding of the everyday world. So yeah, I'm gonna start explaining the duality wave particle with an experiment that was done. It's a really old one. So um, so this experiment consists about two two boxes, one wall, the wall here, the wall here, and basically they come from a machine that is shooting particles. Shooting particles. And you open one box, you close the other, and you just shoot randomly, doesn't matter, 50-50 coming out of these two boxes, and they make a pattern, mostly like this, concentrated all in here, and then the other one kind of the same. Yeah, but what you're doing here is basically open one and the other 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 one and the other. And they just give you this shape that is really logical. When you do that randomly, you will get this frequently. But what happens if you open the two of them at the same time? What happens if you open them at the same time, same moment, and you just activate the machine? You will have something more like this. As you can, what would you interpret of this is that you can see big spots here, and that's not like how it's supposed to be. If you think about it, it will be shooting randomly out of these two boxes and make the old parent of the two big dots, one by the other, but that doesn't happen. And scientists came up with the idea of wave and particles being the same thing, kind of the same thing, that work kind of the same. And this happened because of a still wave. It's interpreting particles as wave, and here still wave are occurring. So I'm just gonna redraw the whole thing up here, smaller. So big groups, like 5 of them here. And what is happening is that when you shoot from a box, from 2 boxes actually, when you shoot from one, you get one wave, let's say like that, and everything is around this area. But if you do the same thing, one wave is just one wave. With this one too, if you can doing this, you will see that they, wait, kind of hard like this. But basically they cancel in these spots and these spots and here too. Yeah, it should was like this, but yeah, basically they cancel. So they work as still wave when they cancel each other, making it no particles in these certain points. And that's why they come up with this idea of wave and particles being the same thing, because of how this experiment behave. And the other way of seeing this is basically percentage. So each particle over here has a percentage to be anywhere in this screen right now, anywhere. But what happens is, because of canceling and adding and blah blah blah, you end up with a certain number. Can be 1, 2, 3, 5. Doesn't really matter. It's basically percentage. And over here you can see that it's lower than here. The number is lower here than here. So that means that there are more probabilities for the particle to hit in this spot than in here, because they're canceling over here. Probably here is around 0.1 something. And yeah, that's the duality wave particle. Actually, I bring the paper. Okay, superposition is the next topic. Superposition is basically that a particle can be something and don't be that thing at the same time. It's your experiment, a Schrödinger cat. Basically one box, portion here. Portion here, you know. Let's see if I can make it scroll. Portion. This portion, and then you have a cat inside here. And that cat can die, basically. There's a timer. Saying whatever time. So when that timer occurs to be over, the glass is gonna either open or not open. And when that happens, this box is closed. You cannot see it from the outside. You don't know what is inside. You basically have 15% to be dead and 15% of be alive. It's basically 50-50. You don't know. You actually don't know. So this cat right now is dead and alive at the same time until you open the box. When you open the box, you are gonna get a dead cat or alive, and that's basically a percentage. It's 50-50 right now, but it can be like, I don't know, 60% dead and then 40%. 60% alive and then 40% dead, and that's totally possible. Basically, you have more percentage to be alive than dead if you play with the average. So how is this translated to particles in quantum physics? Basically, an electron can be in two places at the same time and will be totally possible. If you have an electron here, he can be in this area, in this whole area, or basically the whole. Actually, no, I'm gonna make it easier for me. In this space, he can be whatever he wants. Right now, I found it here, but if I don't look at it, he can quickly move here in this spot, and will be the same electron. But it's in the same, in both places at the same time. But I actually haven't opened the box. I haven't opened it, so I don't know where the electron is. I just know that it's here. It can be here, or it can be there, or it can be here. That doesn't really matter. It's just an electron that we don't know the position until we open the box, and it's uncertain. It's a quantum. It's a superposition. So, yeah. Superposition. I just play it like crap. Okay, third and final explanation. Quantum stage. Quantum stage. So I'm gonna use neutrons. For these experiments, and so they can be square, circle, or they can be color or no color. Easy explanation like that. And you have a machine. You have one machine that picks the color, and then the other that picks the shape. Basically, and you know you basically throw them through the machine, and the machine basically split them apart, giving one that the color ones are 50%, and then the non-color they are 50% too. So 15-50, and then the shape, same thing. Can be a square, that's a rectangle, but it can be a square 50%, or it can be a circle 50%. Yep. 50%. That's basic stuff, you know. You have two probabilities, you basically split them and you get this 50%. Yeah. But what happens now when you you define them already? What happens when you know the color that is gonna be? You already know the color, but you don't know the shape. And you basically have a machine over here that is shooting shape over here, shape, and then shooting shapes. Yeah. Here they're shooting squares. Here they're shooting circles. And this machine over here is gathering this gathering over here all this information and basically making an outcome out of this and picking which one is actually coming out of here. And what you will think is basically 50-50. That will be, you know, obvious answer that happened over here, basically shooting 50-50. But it doesn't happen like that. It occurs that it picks one shape, doesn't matter, and it turns out to be 100% that shape. Yeah, 100% that shape. And why this happens is because we didn't make a define. We didn't define the shape before. So like I say here, we put squares and circle here, but really we haven't defined. We're just saying that okay, we're splitting in two, so I guess we're shooting two different shapes in each line. Friendly. But no, what happens is that we get 100% of one shape. Why it picks that quantum stage instead of the other? It's because of uncertainty. That's the name. Uncertainty. Yeah, and when we don't know the color either, we only know the shape. What is the shape, but we don't know the color. But if we try to look for the color, if we actually try to search for which color is gonna come out of here, we try to get the colors, and we already know the shape. We're gonna shoot out squares, both sides. But what color is gonna come out of here? Well, that basically is 100% of that color. And right now we know the shape. We know which shape is gonna come out of here. Actually, it's not the same shape; it's a different one, circles. But it's gonna be the same color and different shapes. Why because we defining the shape before we send them here in this machine that is supposed to pick colors. Yeah. So what you can get out of the experiment, that when you're trying to search for a particle, you can either share for shape or color. You cannot know them at the same time. You know exactly if the particle is a square or circle, or either color or non-color. You can only know if it's a square, but you don't know which color it is, or you can know the color but not the shape, and that's quantum stages. That should work. I mean, I don't know. Probably did it worse, I think.